Okay, let us see some more examples. The first example is similar to the one that we did on example 1. Only the thing is the damping force is different. Previously we had 12, now it is 17, right? All the other things are similar. So let us first list the given thing. So you have W equals to 16, right? And what else? L is 8/9. The external force is 0. The damping force is 17. And the velocity what is the velocity? Is 2 feet per second, right? 2 feet per second. So now we will try to find out the some of the parameters we need for the equations, right? So if you do W equals to mg, this implies 16 equals to m times 32. That will be implies m equals to 0.5. Similarly, to find out the k to our equation, we do we basically do mg equals to kl, right? This implies m is 0.5 times g is 32 equals to k times 8/9. This implies k equals to 18 as before. And finally, we want to find out the damping coefficient, right? So f d equals to gamma times y prime, right? This implies 17 equals to gamma times y prime is 2. So this implies gamma equals to 8.5, right? So if you use all these values to the equation, so the equation of motion becomes m times y double prime plus gamma times y prime plus k times y equals to 0, right? So this will imply 0.5 times y double prime plus 8.5 times y prime plus 18 equals to 0. And then what is the initial condition? Y at 0 equals to -1/2, because it is at the beginning the mass or the object is displaced 6 inch above. That means in terms of the feet, it is 1/2 feet. Since it is above, so it is the negative direction. Also, you have y prime of 0. Y prime at 0 equals to 1, right? Because it said the initial velocity is 1 feet per second. Okay, so next we want to find out so if you simplify this and if you so you can say to find the eigenvalues, what you do, you solve y double prime plus 17 y prime, right, plus 36 equals to 0, right? So basically eigenvalues, we solve eigenvalues of this. If you simplify, you'll get this one, right? We do lambda square plus 17 lambda plus 36 equals to 0, right? So if you solve it, so we cannot get factors. So if you solve it using the quadratic formula, you will get lambda equals to -2.47. You can use the quadratic formula to find out this. 92, and the other is -14.5208. So what I did is I used the quadratic formula to solve this. Okay, So here, so we got two distinct real and negative eigenvalues, right? So when the eigenvalues are negative, then the motion it will go to zero, right? It will basically it will be stable. So the 0 will be stable basically. So what happens there will be the zero value, meaning the the motion will end. I mean the oscillation will end. Oscillation will stop. So distinct and real eigenvalues. So the solution is you can write y of t equals to, you get c1 e to the negative 2.48 t plus, I'm just rounding up, e to the negative 14.52 t. That is the solution. But using the initial value, what do you get? You get this implies, how do you use the initial values? You find out the derivative of this, and then you use the initial values. Y0 is negative 1/2 and y prime equals to 1. If you do that, you will get initial value as your C1 will be negative 519.519, and then C2 will be, and C2 you will get 0.0199. That is the initial condition, right? So if you plot this solution with this C1 and C2 value, then you will get the overdamped case. Okay, although we are overdamped in this case, it is actually takes longer for the vibration to die out than in the critical damping case. Sometimes this happens, although it will not always be the case that overdamping will allow the vibration to continue longer than the critical damping case. So basically, if you plot this equation, you will get some sort of vibration there, right? And then it will go to the 0. So also you notice that as the critical damping case, we don't get a vibration in the sense that we usually think of them. Again, the damping is strong enough to force the vibration to die out quick enough so that we don't see much, if any, of the oscillation that we typically associate with vibration. Okay, so basically the final solution is y of t equals to negative 0.519 e to the negative 2.48 t, and then plus 0.0199 e to the negative 14.52 t. This is the solution. Okay, let us go to the next example. In the next example, you see that this is similar to the above. Let me list all the given things, and then I will skip some of the steps. W equals to 16, L equals to 8/9, F equals to 0. What is FD? FD is 5, right? FD is 5. And what is Y prime? Equals to 2. So everything is same. So as above, we will get M equals to 0.5. We get that. Also we'll get K equals to 18, right? But you get, if you use FD equals to 5, you will get 5 equals to gamma times Y prime is 2, right? So this implies gamma is equals to 2.5. That's what you get. Okay, so this is basically so what case do you see here? How do I check whether this is underdamped or overdamped, or or the critical damping, right? See that since you get gamma over 2 root under km equals to 6, which is greater than gamma, we see the the case of under damping, right? Case of under damping. So how do I get this? If you look at the notes that we covered in the class, not in the video, if you look at the case, there were several cases, okay? If gamma is greater than 2 square root of km, if gamma is less than 2 square root of km, and if gamma is equals to square root of km, they were under damping, over damping, and then critical damping case, right? So here, since gamma is bigger than 2 square root of km, it is 6 times bigger basically. Since that is the case, it is the case of under damping, okay? In the under damping case, so if you now let's plug in all these values in the equation, you will get, so the equation of motion is, what do you get? If you plug in all those values, you will get y double prime plus you get let's see what you get. You get 5y, right, plus 5y, right, and then plus 36 equals to 0, right? Now if you solve this using the so with the initial condition, you get y of 0 equals to -1/2, and then y prime of 0 equals to 1. This is the equation of the motion. So to solve this, you need to find out the eigenvalues. So for the eigenvalues, what do you do to find out the eigenvalues? You solve lambda square plus 5 lambda plus 36 equals to 0, right? So we need to use the quadratic formula to solve this. How do I do that? You do lambda equals to, you will get this one, -5 plus minus b squared minus 4ac. If you apply that, you will get 119 divided by 2. So this is basically mu plus I nu. Okay, so this is the lambda values, right? So how would the equation look like? So the solution look like, so the solution is, you write y of t equals to c1 and then e to the -5 over t, 2t, and then cosine nu t, right? So what is nu? Nu is 119 over 2t plus c2 and e to the -5/2 t, and then sine nu t, that means 119 over 2t. That's what you get, right? So this is basically the solution. But if you use the initial condition, using the initial condition, so it has the roots. That's why when you use the initial condition, how do you do that? You put y0 equals to -1/2 and then take t equals to 0, and then also find out the derivative, and y prime of 0 is 1, and then solve for c1 and c2. You will get c1 is -0.5, so you get c1 equals to -0.5, and then c2 equals to, you'll get -0.046. That's what you get. Okay, So so this is basically the equation of the motion, right? Now we want to see how it looks like if we change this into the phase amplitude form. That, like, do you remember we substituted like C1 equals to R cosine delta and the C2 equals to R sine delta and so on. If you do that, then you will get substitute C1 equals to R cosine delta and then C2 equals to R sine delta. What do you get? You will get basically R. This implies R equals to under the root C1 square plus C2 square. This implies R is 0.5021. 0.5021. What I did is I plug in the value of C1 and C2 here, okay? And this implies delta equals to pi plus tangent inverse C2 over C1. Because both C1 and C2 are negative, we'll look at the third quadrant, right? If you do that, you will get 3.2321. That's what you get. So you plot that with respect to the time. So what will be the equation look like? Therefore, hence y of t equals to, you will get R is basically 0.05, right? 0.521. Okay, and then how about the nu also? Oh, I forgot to calculate the nu. So how do I find out nu? Nu is basically nu is square root of 119 over 2, right? That's what you get. That is 5.45, and then so the yt will look like R is, what is our R? 0.5021, right? And then e to the 5t over 2, right? That's what R e to the gamma t, right? So that will be 0.5021 e to the 5t over 2, and then cosine 5.40 nu t minus delta. So our value of delta was 3.2321. So this is basically the solution in the another form, right? So the phase amplitude type of form. Now if you plot this equation in your calculator, then you can see that you can see that the motion will die out, right? Also, how do we find out the quasi period? So the quasi period TD, we did that formula in the class. TD is 2 pi over nu. If you do that, it will be 1.1519. So, and then what do you get? But if you find out the T without the damping case, without damping case, that is example 1, right? Case, if you find out the T, that is the what was the T? T is basically the period, right? Period was 1.04. Look at the difference about TD and T. Okay, so the T is constant there. Also here TD depends on nu. Okay, so in this case, if you plot this graph, you will see the true vibration, right? So if you want to find the time at which the object first passes through its equilibrium position, we can do nu t minus delta equals to pi over 2. That will give you the equilibrium position. Then you get the t equals to 0.88 if you do that. Also the stability, in this case the critically damped and the overdamped cases, 0, 0 is a nodal sink. For the case of no damping, the origin is center, while the underdamped case origin is the spiral in. So this is the case of underdamping. So you will see the spiral in case. okay, if you are talking about the stability of the zero, of the equilibrium point 0. Okay, so at the end I want to assign the homework problem. So homework problem is section 4.4. Section 4.4. So question number is 5, 9, 10, 11. 5, 9, 10, and 11. Okay, so the page is let me see what page is that. That will be 250. Okay, so you do these problems and take the picture and send that to me. Okay, guys, by next Monday. So do these 4 problems. They are similar to the one that we just did, and then do all 4 problems, take a picture and email that to me. Thank you.